Like I said, Steve, I believe, is back. Let me see if I can find him again. Yep, he's back. So our next speaker is Michael Harris from Columbia University, and he will speak on ramification of supercuspidal parameters. Go ahead, Michael, whenever you're ready.
Well, thank you very much for this invitation. It's great to have an opportunity to thank Steve in one way or another. And there will be, I missed that 10 years ago, so I have at least the live version. But and there will be a reason to do that. But you won't see very many theta functions in this talk, and I have to apologize to the organizers for that. So this is work in progress. It started just a little over a year ago. I noticed one of my collaborators is in the audience, so you can tell me. All right, so this one has a moral, and then it's going to have some substance. But I'm going to start with the moral. It has to do with the local Langlands correspondence. So see, it's about everything in the title except theta series, representation theory, geometry, and arithmetic. And one of the things I like about it is that it's about all of these. Somehow it's about all of these at the same time, but without really about the theta series. And the moral is that a very simple application of a deep theorem in geometry has surprising consequences for representation theory, or at least it seemed surprising. And not only surprising, but welcome consequences, and I'll say something about that. And specifically for the representation theory of groups over local fields of positive characteristics. So there is something more to be said these days about local Langlands correspondence for local fields of positive characteristic. And the applications are consequences of the expected local Langlands correspondence, which is fortunate. They're not, don't contradict what's been expected. But what is expected? I have to go through that slowly. But I should say that even though there aren't going to be any theta series, my obsession with the local Langlands correspondence was a direct outgrowth of my work with Steve on the theta correspondence. Well, it says a direct outgrowth, and I said not directly, but it still was a direct outgrowth. In fact, if you look at our paper on the triple products, you can find two very obscure allusions to the local Langlands correspondence. It was around that time that I started thinking that it was something I ought to understand better. That's my explanation. And in case I didn't understand what I meant there was a stage direction in case. Anyway, this picture was taken in Japan in 1983, and you can try to recognize the people in the picture, some of the people anyway. The surprise answer is that there is no local Langlands conjecture. Well, or another way of putting it is that there are several local Langlands conjectures, and I'm going to explain why they should all be compatible with each other, but nevertheless, they don't together amount to a local Langlands conjecture, not a meaningful one. So G is a connected reductive group over a local non-Archimedean field with residue field of positive characteristic P, but not for the time being. F is not assumed to be, it can be p-adic. And unfortunately, I have to introduce some notation which was going to disappear. It's pi of G over F is a set of admissible representations with coefficients in some algebraically closed field of characteristic 0. And then a Langlands parameter is a pair. This is a Weil-Deligne parameter. So you have the Weil group parameter, which is a homomorphism into the L group, and then this unipotent element of the Lie algebra. They satisfy the usual relations, which I won't recall. So there, we have the representations, and we have the set of parameters, the equivalence classes. I won't remind you of the equivalence relation is denoted phi of G over F. So there are two objects, phi and pi being the representation, and phi the parameters, which are on the Galois side. So here's the first version. There is a canonical parametrization, which goes from the pi, mapping from the representations to the parameters, such that what I call the L packet, which is not necessarily the proper terminology, the fiber over a given, the inverse image of a given phi, that's what this notation is supposed to be, is finite. And furthermore, it's non-empty. All right. So but all the work in this conjecture is in the word canonical. Problem is, who's canon? Because as André Weil might have said, might have deigned to say that both sides have the same cardinality. You can even partition them in such a way, and the Bernstein components, they also still have the same cardinality. So as stated, is a vacuous conjecture. So I'm going to clarify the conjecture just for the tempered representations, and we'll sometimes, probably even always, forget the superscript. So let's try to understand what the conjecture says about tempered representations and tempered L packets. Well, first property, there's a list of properties. I'm going to go through these pretty quickly. When G is a torus, the parameterization is given by class field theory, particularly for GL1 and generalizations. I won't read the details. If you have an isomorphism of fields, then the natural diagram with the where you have the change of field on the Galois side and the change of field on the representation side commutes. Okay. More conditions. Let's take a homomorphism of algebraic groups to a torus, and then we get a dual map of L groups, and then it is this parameterization is compatible with twisting, where here you've got to take the Langlands correspondence for the character. Here you just tensor the representation by the character, right? And this is a multiplication. It's compatible with taking contragradients when sigma is any homomorphism. When you take the homomorphism of algebraic groups, because you have you can compose the parameter with a homomorphism, and you can compose the parameter with the homomorphism on both sides. Central isogenies. This, I won't say the details. It's compatible with central isogenies. And then some more properties I will go through very quickly. It's compatible with products. It's compatible with normalized parabolic induction. That's a big one, but it takes up too much space on the slides, so I won't write it down. Compatibility with restriction of scalars. That means if you see the same group, if you view the same group as a group over two different fields, a field and by restriction of scalars over a subfield, then the correspondences are compatible. Now, some substance, it's compatible with a Satake correspondence for spherical representations, which is where the whole thing started, which is, part of normalized parabolic induction. And now, suppose the representation belongs to the discrete series, specifically supercuspidal, which are going to be the ones I talk about. Then the quotient of the centralizer of the parameter by the invariance in the centralizer of the dual group is finite. So that doesn't say very much about it, but it's important. This long list still does not get anywhere near a characterization of L, and the real issue is the supercuspidals, because if you just have a bijection of supercuspidals, that's the same cardinality on both sides. Supercuspidal with irreducibles in whatever that means. Let's continue. There are also some automorphic, those were structural conditions. There are also some automorphic conditions. So very vague. Suppose there's a theory of automorphic functions attached to the group G over the field F, and this homomorphism to a general linear group. So for example, so F could be a local field, but it really should be a global field as well. It should be a local field viewed as a completion of a global field. So for example, the Rankin-Selberg method or the Langlands-Shahidi method, any method you like to construct automorphic L functions, then whenever you have there's this additive character in there, which I forgot to explain. Maybe it's on the next slide. So it's compatible with endoscopic transfer. It's compatible with, oh, yes, I think at the end of this, I erased it because it was taking up too much space. What I wanted to say is that there's compatibility with L and epsilon factors, local L and epsilon factors, one on the Galois side and one on the automorphic side. Should also be compatible with cyclic base change. So this is a version, a particular version of endoscopic transfer, twisted endoscopic transfer, and then local global compatibility. So this is an automorphic condition that says if you have, in addition, a global Langlands parametrization, if you're starting with automorphic representations or cuspidal automorphic representations, and if you can attach to that a global Langlands parameter, then the restriction of the global Langlands parameter to the decomposition group of a given place is equivalent to the local correspondence. That one would take up 2 slides. I didn't. Anyway, it's an important property that is known in all cases. So point 1, which was the thing that was erased, compatibility with L and epsilon factors, together with some of the earlier conditions, actually suffice to characterize the local Langlands correspondence for GLN. So there's only one that satisfies those conditions. That was proved by NER. So we can talk, it makes sense to talk about the local Langlands correspondence for GLN, for general linear groups. Point 1 is, as far as anybody knows, useless for E8. Nobody has yet found a theory of automorphic L functions for E8. So that's not going to get us past the ambiguity. So point 3, on the other hand, makes sense for every group in positive characteristic because Vincent Lafforgue has given a global parametrization. And moreover, well, what he's given is a semi-simple parametrization for global representations, and Genesti and Lafforgue have proved that the global parametrization has a purely local definition. But the original
Michael, sorry. So your point 1, so you said E8 point 1 doesn't do anything. So do you mean for other exceptional groups you can actually use point 1 to characterize?
Well, I don't know whether you can characterize it, but at least you can hope to characterize it. For the other exceptional groups, there are both Rankin-Selberg and Langlands-Shahidi L functions for E6 and E7. Well, not for F4, you may be able to sneak by with the endoscopic transfer, and G2, well, G2 there are automorphic L functions. And but let me remind you of the original conditions. That is, there's the canonical parameterization. That means that it better satisfy all those conditions, and that means in particular that the conditions are not mutually exclusive. And we want to know that the L packet is finite, and then that the L packet is non-empty. So the results that I'm going to be talking about with my collaborators do not yet help with B and C, but they suggest a few directions. They eliminate some of the worst possible pathologies. So that's what I'm going to get to. But let me talk about, there are a few other canons. There are other canons that or purported correspondences or parametrizations, at least, that claim to be correspondences, that Fargues-Scholze for p-adic fields has a construction that is completely parallel to the Genesti-Lafforgue parametrization. But in general, there's no corresponding global correspondence, nor would is anybody in the present decade likely to find one, although we never know. So there's no, you can't ask about local global compatibility, and that's really important because that has a lot to do with characterizing the correspondence. So finiteness of packets and surjectivity of the parametrization are not known for either Fargues-Scholze nor for Lafforgue. In principle, it's possible that infinitely many supercuspidals, this is the sort of thing that if you were the sort of person who's kept up at nights worrying about these things, might worry about this. It's possible that infinitely many supercuspidals have completely trivial parameters in either case. But we can exclude that by our methods. So at least that is not going to be a worry in most cases, practical cases. Then there's Kaletha's parametrization, which is based on a completely different principle, based on the construction of JKU, which gives most supercuspidals the domain. It doesn't give a complete parametrization. The domain is only the set of regular and non-singular supercuspidal representations. But by Jessica Finson's results, this does include all supercuspidals for almost P. And if you're willing to admit that for classical groups, everything can be handled by transfer to GLN, then this really only, for exceptional group, this only leaves P less than or equal to 7. And furthermore, the three authors listed there, recently proved character formulas that imply compatibility with endoscopic transfer and thereby give a unique characterization of the parametrization, except for a small p, where the methods apparently don't work. Nevertheless, so there you've got a canon. Is it the same as either Fargues-Scholze or Lafforgue? So it would be really uncomfortable if there were two canons that gave in different p's. I don't know, it's a question whether this sort of thing is accessible by Lefschetz trace formula techniques. Maybe somebody in the audience knows the answer to this. Well, here's another question. Suppose you have a p-adic field and then a local field of positive characteristic, and suppose they are close, of n close, which means an isomorphism of truncated integer rings. Deligne showed that the Weil group parameters of the corresponding depth, which is defined in a natural way, are in one-to-one correspondence, a natural bijection. Now, suppose G is split connected. Maybe this is not strictly necessary, but at least it's necessary. It's useful to make the statement concrete. And suppose you have the standard congruent subgroups of level prime to the rth power. Then you can define the corresponding Hecke algebras, for these congruent subgroups for the two fields. And Kazhdan proved that if they F and F sharp are n close for some n that's larger than R, then the irreducible representations of depth R are in correspondence. Okay, so here's an exercise. If n is bigger than R, this diagram with a Genestier Lafforgue correspondence on top, the Fargues-Scholze correspondence on the bottom, the Kazhdan correspondence on the left, and the Deligne correspondence on the right commutes. And the challenge is to prove this conjecture. Okay, I don't know whether that's an accessible question or not. This is Steve looking very pensive, maybe thinking about the challenge in the background. But actually, what this is just that the photo is blurred. I think his eyes are actually open. Okay, let me now review Vincent Lafforgue's global results. So now we're going to be working over a smooth projective curve over the field of Q elements, and L is a prime different from P. In order to avoid complications, let's say G is split semi-simple over the function field of Y, and then let's let A0 of G be the set of cuspidal automorphic representations of G over this of the adels. And then we consider semi-simple maps from the Galois group of K to the dual group. By semi-simple, I mean if the image is contained in a proper parabolic, then it's contained in a Levy subgroup. Standard definition. So here's Vincent Lafforgue's theorem. There's a map, also called L, from automorphic representations to semi-simple parameters with the following property. If at least the following property, suppose you have a place, point, and pi as a cuspidal automorphic representation unramified at that place, then Lafforgue's parameter is unramified, and the semi-simplification restricted to the decomposition group or the V group at V is the Satake parameter. So in other words, this is compatible with the Satake parameterization at unramified places. Right? That's part of his big theorem. And then the Genestier-Lafforgue paper says that if you define, suppose you have your pi as above, and suppose you go out on a limb and say that you define a local parameterization for the local component of pi at W by just taking the global parameterization, restricting it to the V group at W and semi-simplifying, then this is well-defined. It depends only on the completion at W and on pi W and not on the globalizations. Moreover, it's compatible with normalized parabolic induction. So that's pretty good. You've got some of the desired properties. So in particular, you don't have to, your pi, your representation, an irreducible representation of the group of the local field, it doesn't have to be realized explicitly as a component of an automorphic representation. You can work around that. You can define a semi-simple homomorphism from the V group, the local V group, to the dual group. And that's the local parameterization. That's the Genestier-Lafforgue parameterization. Now, one thing you can do with V group parameters is look at weights. So suppose you have a global, now this is wrong. This is the, oh yes. Okay, suppose you have a linear representation of your dual group, and pi is your automorphic representation. Let S be the set of primes where it's ramified. Well then, composing the parameter with sigma gives you a semi-simple L-adic local system on the complement of S in a curve. So it's in other words, it's unramified outside S. The local system is unramified outside S. Now, by Deligne's V2, which is the deep geometric theorem I mentioned at the beginning, each irreducible summand of this local system is punctually pure, up to, that is to say, it has weights, integer weights, but you might, because this is over a finite field, you may have to twist by a character of the Galois group of the constant field extension. Let's not worry about that. So for any W, the eigenvalues are VQ numbers of various weights. The eigenvalues of Frobenius at W are VQ numbers. This is even true at the ramified places. You have to choose a Frobenius at a ramified place, but still, you choose it. The eigenvalues are VQ numbers of various weights, up to the twist, which is, the norm to the S sort of thing. So let's say a representation pi of the local group G of F is pure if for some, or equivalently for any faithful sigma, the eigenvalues of Frobenius after composition with sigma of the parameter have the same weight. All right, so we can introduce a notion of purity for these representations of the representations of the local field, group of local field. Well, if G is not GLN, not all supercuspidals are pure. Here's our main theorem. Remember, G is split semi-simple. There should also be a version, at least for quasi-split. Suppose we have a pure supercuspidal, and suppose it is compactly induced from a compact open subgroup of G. For example, if P does not divide the order of the Weil group, this follows from Vincent's theorem. Suppose, moreover, that Q is bigger than 3. This is not about the residue characteristic. This is about the order of the field, and this is probably temporary restriction. Then L of pi is not unramified. So if you have a pure, that is to say, it is ramified. That is to say, the restriction of the parameter to the inertia subgroup is not trivial. So that's in order to avail ourselves of Vincent's theorem, we assume that P doesn't divide the order of the Weil group, so every supercuspidal is going to be compactly induced. Then by induction on parabolic subgroups, and because L is compatible with parabolic induction, let pi be a pure representation of any kind, not necessarily supercuspidal. And suppose the parameter is unramified, then pi is an irreducible constituent of an unramified principal series. So at least we don't have to worry about infinitely many supercuspidals with trivial parameter. Okay. Now, this is, suppose we have local and global cyclic stable base change over function fields, and it's as in the restricted sense worked out in Basse's book. So suppose we have it globally for certain classes of representations. So he considered the representations with some Steinberg constituents, which is fine. So then we can say a representation of G of F is incorrigible if it's supercuspidal and such that no matter how many times you try to make it stop being supercuspidal by cyclic base change, the base change, which is an L packet, which could be infinite because we're defining the base change in terms of global representation, if it still contains a supercuspidal member. A corollary, assuming the existence of base change, no pure supercuspidal representation is incorrigible. Well, this fact, people who work in the local Langlands correspondence are well aware that this was really the key step in the proof of the local certainly the key step in the proof of NER's numerical correspondence. And with this, together with properties of base change, you get the local and twists under base change, you get the local Langlands correspondence. That's basically how NER proved the numerical correspondence. If you have a canonical correspondence with this property, then you get the local Langlands correspondence. And there are two proofs of this corollary for GLN. NER proved it by the numerical correspondence, and that's used in in most of the proofs of the local Langlands correspondence. Scholze gave a different proof using the geometry of nearby cycles on the Lubin-Tate moduli space. And as I just said, along with the existence of a canonical parametrization, this is the key step in any proof of local Langlands correspondence. Last year, Sian Daniel Lee Huertu, I think is in the audience, a third-year student at Harvard, gave a new proof for GLN in positive characteristic, modeled on Scholze's proof for p-adic fields. And again, this is the corollary, the key step. All right. Here's another result that we get by our methods. Suppose pi is a pure supercuspidal that's compactly induced from an open compact subgroup that is small in an appropriate sense. Then L of pi is not only ramified, it's wildly ramified. So an example of small open compact subgroup is the principal congruent subgroup. Remember, we have it's split semi-simple, so the principal congruent subgroup as defined by Chevrolet basis. And we can even say something about the supercuspidals that are not pure. Well, if they're not pure, the Langlands parameters should be, well, actually, that's a false. They should have Langlands parameters. That there should be a should there. They should have Langlands parameters rho n with n not equal to 0. They should have a non-trivial monodromy piece. These are like unipotent supercuspidals. Well, we would expect that the pair rho n satisfies the property that's in arithmetic geometry known as purity of the monodromy weight filtration. Again, up to this unramified twist so that we can make sure our weights are integral. Well, for any first of all, for any linear representation of the dual group, the eigenvalues of Frobenius are all Q numbers of integer weight. The subspace of eigenvectors with eigenvalues of weight less than or equal to A is invariant under both rho and the monodromy operator. And then the key principle. So then you can define n on this associated graded so W is a fixed weight. There is a weight like the central weight such that the map is an isomorphism on this graded piece. Okay. The parameter, now remember the Lafforgue parameter is semi-simple and the Genesti-Lafforgue parameter is also semi-simple. So they're just Weygroup parameters, they don't see n. However, it's easy to see that not every semi-simple parameter with several weights can be completed to one, satisfying purity of the monodromy weight filtration. Suppose, for example, that the composition of rho with the linear representation has two weights. If rho can be completed to rho n satisfying purity, then they have to be of the same parity. It's pretty obvious. So you're not going to get, so if a supercuspidal, if the semi-simple parameter of a supercuspidal is not pure, you would hope that the weights satisfy the same parameter. Well, we prove it can be completed, the semi-simple parameter can be completed to a pair where SS pi is the semi-simple part and n that does satisfy purity of the monodromy weight filtration. So this shows that even if it's not pure, it has a purity property, namely purity of the monodromy weight filtration. We can call this the full Langlands parameter. And with this definition, the Langlands parameter of pi is ramified. It's ramified in n. The semi-simple part need not be, but the n gives you ramification of infinite order of plane ramification. And here's a representation. Here's another theorem that has nothing, well, that's related. It's nothing to do with our methods. Suppose pi is a depth 0 supercuspidal representation, for example, induced from a Deligne-Langlands, a Deligne-Lustig representation of the quotient of the maximal compact of hyperspecial maximal compact by its first congruent subgroup, then is tamely ramified. So this is roughly a very rough definition of depth 0 representations. And the idea of the proof is to use congruences. So this is of Deligne-Lustig representations and also congruences of supercuspidal representations. So this is using model Langlands correspondence, which you note, the point is that wild ramification is preserved when you reduce modulo L if L is different from P. So you can detect it by the modular correspondence. All right, so here's something about the proofs. So let's suppose that our curve is just P1, all right? And then we choose a Borel over the constant field and B minus the opposite Borel. I guess I'm going to slow down because I have some time. So let's let I0 be the Iwahori in B, and I infinity plus be the pro-unipotent radical of the Iwahori corresponding to B minus. You think of 0 and infinity as being 2 points on P1. So now we're going to construct a cuspidal automorphic representation with favorable properties. First of all, we have our pi. Remember, we have our supercuspidal pi, a pure supercuspidal. And at every rational point over the constant field, other than 0 and infinity, we make this, we want the automorphic representation to be our chosen supercuspidal. For the points that are not rational over the base field or the ground field, pi is unramified. And then it has a fixed vector under the pro-unipotent Iwahori, the pro-P Iwahori at infinity. And then at 0, it contains a vector transforming under a certain character of chi called chi k, which is not the same k, I'm afraid, but it's a character of the of this. It was a character of this torus over a finite field. As I say, this is what you think it is. This is the pro P Iwahori at 0. All right, we're going to construct such a cuspidal automorphic representation. And if we can do that, then now suppose L of pi is unramified. Well, by the purity hypothesis, that says that for any faithful representation, remember the parameter, so L pi sigma, which means sigma composed with L pi. I think I didn't introduce that. A priori, so an L-adic local system on P1 away from the rational points, because if at the points outside, at all these points outside of P1 of K, the automorphic representation is unramified. So it's an L-adic local system away from the points places where pi is ramified, capital Pi, but because it's pure, it extends to punctually pure local system on GM, that is to say on P1 minus 2 points. And why is that? That's because there could have been unipotent monodromy at the rational points, because all we know is that the semi-simple parameters is unramified. But because there's no unipotent monodromy, because it's pure, there's no monodromy at all. So we have we have a local system on GM. And moreover, our hypotheses that there are fixed vectors under pro P equal Hori imply that the ramification at 0 infinity is tame. Well, we know all the local systems, all the tame local systems on P1 minus 2 points. It's the sum of local systems induced from characters of finite order of the tame fundamental group of GM, which is just Z, well, Z hat away from P, not including P. But L pi of Z, that is to say, for every Z in the rational points, we know that it's L of our chosen pi because they're all isomorphic. But by varying the character chi, we obtain a contradiction. I won't give you the details of that. So it's the kind of Gauss-sum argument. So now we're going to construct this capital pi. So suppose for simplicity that pi is compactly induced from the integer points, the group of integer points. This is the easy case. Suppose let phi of pi be a matrix coefficient supported in U. That's what we're allowed to do because it's compactly supported. And we suppose that for simplicity that phi of pi of 1 is 1. And construct Poincaré series, as in the paper of Gan-Lomélie, where we choose data at every place at at every Z in the rational points, it's this chosen phi sub pi, our supercuspidal matrix coefficient. For X not rational, it's just the characteristic function of the integer subgroup. At infinity is the characteristic function of the pro P Iwahari subgroup. And at 0, it's this character, chosen character. The support conditions, and you just look at which elements of the adels lie in this product of groups, and you see that that it's not 0. That's important. You want to prove Poincaré series. It's easy to construct Poincaré series that equals 0, but here we got one that's not 0. And then we set pi to be the translates of this Poincaré series. Well, then the conditions are pretty clear. It has a fixed vector under this group, and it translates by character under this group, and then at the supercuspidal points, it's the L of pi. It contains it. It is pi. It is our pi. So the assumption that pi was compactly induced from our integer points allows us to choose the local groups at 0 and infinity very simply. And in general, one needs to look more closely at the building to guarantee that the appropriate support conditions so that the Poincaré series is not identically 0. Well, the case of reductive G reduces easily to the semi-simple case, and we have not looked seriously at non-split G, although we hope to generalize it at least to quasi-split groups before we complete the paper. But WeTech reminded me that if X is an F variety with G action, one may form the X theta series just as this sum. And if X is just G with G acting by translation, then theta is the Poincaré series. So yes, it is a theta series. It's not the kind that figured in my papers, my joint papers with Steve, but it's legitimate for this conference after all. All right, let me say something about the wild ramification. It's the same basic idea. So suppose it's induced from a small open compact subgroup, and it's wildly ramified. Well, as before, we get a non-vanishing Poincaré series, but now because the subgroup is small, we get an extra condition at infinity. So it's or at 0. So it's unramified outside infinity. So it's a local system on A1. Now, by the previous theorem, L of pi is ramified, and since there are no tamely ramified local systems on A1, the ramification must be wild. Yes. I don't know what. Yes, they're more general small open compacts. I don't know what more general means here. I'm not sure what I was you have to read what my mind was when I was preparing this slide. And now for the mixed supercuspidals. But now things are, we don't actually have to use compact induction. So this is completely general. We start with any supercuspidal pi and we globalize to an automorphic capital pi such that LSS of pi is irreducible under the adjoint representation. That is to say, that is, that's not a Lafforgue's parameter. Global parameter is irreducible. Now here we don't even have to work with P1. Take a curve with points x, y, and z, and pi, capital pi, with pi sub x being our chosen pi sub y being the Klosterman representation considered in the paper of Heinle, Ngo, and Yoon, for which it's known that the image of the local parameter, this is the Geneste-Lafforgue parameter, is irreducible. There are some exceptions for small primes. And what is z? I forgot to say what z is. Maybe I'll remember that. We choose z so that it's I guess it's I don't remember what z is. I think it has to be Steinberg is z. Yes. So then a result, yes, Steinberg is z. Then a result of Salwin and Tempier generalizes purity of the monodromy weight filtration to G hat parameters. And it implies that the Deligne parameter of the restriction of x to x of the, okay. So we take, let me slow down. We take the global parameter, which is irreducible, and therefore, by this result of Salwin Tempier, at every point, the restriction satisfies purity of the monodromy weight filtration. In the sense that when you compose, so this is purity of the monodromy weight filtration for G hat. So the semi-simple parameter, L of pi, has the completion, namely L sub x of pi, LSS of pi at x, this restriction. So if it has a completion, then in fact it's unique. It's the only completion that satisfies purity of the monodromy weight filtration. So again, this is a construction by Poincaré series. Here, by the way, is the proof. I'm not going to explain what this means, but this is the argument that allows us to conclude or to find a contradiction, draw a contradiction from the assumption that all of the local parameters were unramified at the supercuspidal points were unramified and equal, GM. So this is the kind of argument you get. This is basically Kummer theory. Now, so in the remaining few minutes, I want to say how this could help to prove the local Langlands correspondence in general. So start with an irreducible parameter. We want to show, let's just say we want to show that this irreducible parameter is in the image of the Geneste-Lafforgue correspondence, which would have to be in the image of a supercuspidal, because the correspondence is compatible with parabolic induction. So we start with an irreducible parameter. Then the methods of my paper with Buchla, Kari, and Thorne allow us to define a global Galois representation with some properties. So we've got a curve. First, the restriction to to the local decomposition group at some point x is our chosen parameter. The image of the global parameter, the global Galois parameter, is Zariski dense in the dual group, and this Galois representation becomes automorphic. That is to say, it's in the image of Vincent Lafforgue's correspondence if you replace y by a finite Galois cover. All right. So we want to show that rho is in the image of the local correspondence. But remember, having taken this Galois cover, we may have lost everything. We may have lost all the interesting information in rho, because we have no control over the ramification of y prime at the point x. What we do know is that, well, let's first assume that there's stable base change for G, and we can replace y prime, or up to replacing y prime by another Galois cover. We can assume that tau prime is unramified everywhere. All right, so now, so we have an unramified parameter that is the restriction to a Galois cover of the global parameter that has the interesting local parameter. Now we want to descend, that is to say, the reverse of cyclic base change, step by step along a decomposition group over the point x. If we can do that, then by Chebotarev density, necessarily, if we can descend our tau prime to an automorphic representation over the fixed field of the decomposition group, then necessarily that automorphic representation locally at the fixed point, at the point above x, is a supercuspidal with our chosen parameter, or starting parameter. So you want to realize starting parameter. Oops. So suppose pi prime has multiplicity 1. Okay, that's then we can at least descend over the center of the decomposition group. That's actually, assuming there's cyclic base change. The multiplicity 1 hypothesis is unknown for general G, but would follow from a similar hypothesis from the geometric Langlands correspondence over the algebraic closure of so f q bar of y, the curve over the algebraic closure. And there are these long papers deriving, reconstructing the Vincent Lafforgue's parametrization from the geometric Langlands correspondence. So if the geometric Langlands program can be carried out for function fields of curves over for the positive characteristic, then there's the multiplicity 1 hypothesis is safe. And now we have an inductive proof. So induct on the dimension of G and assume endoscopic transfer. Okay. Now there's some technical terminology. We assume that the R groups defined automorphically, which have to do with the local intertwining of induced representations, are isomorphic to the R groups defined in terms of Galois parameters. This is a conjecture. The R groups defined in terms of Galois parameters have to do with the centralizers of the Galois parameter. So these are technical. There's a conjecture that these are the same. Is it Shahidi's conjecture? I'm not sure. Then it's known for most classical groups. And finally, we assume there are no pure incorrigible representations, which and we can get away with that if P doesn't divide the order of the eval group now. Then all representations with pure unramified parameters are constituents of unramified principal series. Then, as in the proof for GLM, this should be the key step. It seems plausible that the strategy used by Arthur to construct tempered L packets for classical groups can be applied inductively to this base change situation. This involves techniques that I am struggling to understand. I hope to have something more to say about this by the end of this year. And then we could just reconstruct the L packets by successive cyclic descents. That's the end, and that's all I have to say. And thank you again, and thank you, Steve, for everything.
All right, if we would like to unmute and thank Michael for his talk, that would be fine. All right, do we have any questions for Michael?
Yes, Michael, I may have missed this during your talk, but can you say anything about these packets, tempered packets, which have both discrete series and supercuspidals in them?
Not a whole lot, no. All I can say is that, I mean, we have not, what we can say is that undoubtedly those are the ones that are not pure, whose Ray group parameter is not pure, but whose Deligne parameter satisfies purity of the monodromy weight filtration. But we can't identify those otherwise. I mean, you know, I think that's a trace formula question.
Thank you.
By the way, in the paper of Taylor and Yoshida, they prove purity of the monodromy weight filtration for the global realizations, that is the local global compatibility for discrete series that are not supercuspidal, and they call the parameters pure. They don't say that so this, and I was looking in the literature, there doesn't seem to be a one-word term for a parameter that has purity of the monodromy weight filtration, and saying it satisfies purity of the monodromy weight filtration is kind of cumbersome. So if anybody can come up with a better terminology, please let us know.
All right. Are there any more questions for Michael? Well, I don't hear any, and I don't see any in the chat.